Hi, I'm Vongphasouk, and with my partner Luc Lafave, we developed a device called the Pi-Speed Siren. This device aims to record data from an accelerometer and use it to determine the speed the device is traveling. Once a certain speed threshold is crossed, the device will then give a siren-like signal using pulse width modulation. The user can also adjust the speed threshold for the siren activation. Taking a closer look at the hardware, there are 6 main smaller devices used. For initial parameters, we use a potentiometer and analog to digital converter to get a speed from a specified range. There is also a reed switch to turn the device on and off. For data collection, an accelerometer is used to get acceleration and velocity as a result. For sensory output, we have a buzzer and LEDs that follow pulse width modulation. For more clarity, a circuit diagram is provided highlighting the connections on the breadboard. Now here's Luc to explain the software side of the device.
All right, here's our code. So first we import some libraries, we set up some pin numbers, we also set up for PWM parameters and instantiate some lists and the speed threshold. Then we start a program which is just a repetitive while true loop where we record the past time as whatever time is currently happening. Then when the reed switch is connected to the magnet and we enter this, we get the current time and we find the change in time, which is the current time minus the past time, and we get our acceleration. If the acceleration is over a certain threshold, then we will want to update our velocities. How we update our velocities, we have the previous sum of the velocities plus the acceleration times the current change in time. Essentially, all this does is it implements an integral. Once we have our velocities, then we want to square the two velocities in both the x and y directions and find the square root. This will give us our overall total speed. We also set our past time equal to our current time, so we know the change between our first recording of acceleration to our next one. If our speed is over whatever our potentiometer reading is times our constant speed threshold, then we'll activate our siren, which is the lights and the buzzer. If not, we'll turn our lights and buzzer off. Once we disconnect the reed switch, then we'll turn everything off and we'll save all our data into an MP file. We also can show this MP file down here as graphs that you'll see in the next slide. All right, now into our graphs. On the left is our velocity versus time graph, and the right is our acceleration versus time graph. When our acceleration is a constant positive, we have a constant positive change in velocity. When our acceleration is a constant negative, we have a constant negative change in velocity. This demonstrates that we implemented our integral correctly. We also saw that at the positive and negative peaks of velocity, we had our siren active, while in the center, we had our siren inactive. That shows we implemented our if thresholds correctly.
Now here are some demos and resulting graphs to help showcase the device. The first clip has the potentiometer set low, therefore having a low velocity threshold. This is the resulting graph from that test. As you can see, the trends followed from what Luc had described and had crossed the speed threshold. This second clip has the potentiometer set high, therefore having a high velocity threshold. This is the resulting graph from that test. Both demos were conducted similarly and have similar results. However, the siren did not go off in the second test as the speed threshold was higher.